Hi everyone, a very good afternoon present here. And I'm sure that you enjoyed all the interesting talks earlier today. Not very impressive like other speakers, but let me just introduce myself. Myself Shuchana, I'm Shuchana Datta from University College Dublin. And I'm a doctoral student over here. So like Debashish and Pracheta, I am also primarily interested in information retrieval, like all the models and its applicability to optimize retrieval effectiveness. However, I believe that whatever problem that we are dealing with, like whatever may be the models, it is never desirable that we use that model like a black box, right? So we always want to dive into it, irrespective of your model accuracy, maybe high or maybe low. So I'm sure you already got motivated by Debash's beautiful and insightful explanation, like why we need to explain our model, right? And you also got to know that how to learn to explain your model from Pracheta's talk. And that was very interesting. So now today I'm going to introduce you to explaining machine learning models with Shapley values. So Shapley values are a widely used approach, you can say, from which comes from cooperative brain theory. And throughout this session, I'll be trying to help you build a clear understanding of how to compute and interpret this Shapley-based explanations of like machine learning models. So apart from all these mathematical terms and technicalities, we'll also look at like how SHAP, it's a Python package that I'm going to explain to you later on, that helps us to interpret simple to complex models with the help of Shapley values. So let's just get started with model explainability with Shapley. Pardon. So this is kind of the brief overview of our session, of the session. And first we'll just try to know why do we need the Shapley values? Like we understand that it is very important to get into the model itself, like what are the features, I mean, how your features are behaving into your system, and I mean, what are their average or in total payoff to you, or the contribution to the overall model outcome. But why do we need this Shapley value? Then I'll have a brief overview over the background of this Shapley values, like why it was introduced first. Then I'll have a brief description on the cooperative gaming, like where the Shapley, this concept of Shapley's actually was in action. Then I'll talk about the Shapley values and how it is related to the machine learning problems while you were exposing your models, while you were actually operating your models and all the features associated with it. And then we'll see how to compute Shapley values, all its mathematicals and technicalities over there. And lastly, we'll have a closer look to your model using the SHAP, the Python package itself. So let's get started. So if I ask you a question, like, could you explain this? Like, if I give one situation, like assume following scenario, like you have trained a machine learning model to predict apartment prices. And for a certain apartment, it predicts that the average price is 300,000 euro. And you need to explain its prediction. So the apartment has an area of, I mean, these are the features that are provided here. The apartment has an area of 50 meters square, and it is located on the second floor. It has park nearby, and the cats are banned. And the average price, it has been predicted by your model, is 310,000 euro. So now the question is, how much has each feature value actually contributed to the prediction compared to the average prediction? Now, in the real world problem, we consider that prediction can be explained by assuming that each feature value of the instance is a player in a game, where the prediction is the total payout. Now, Shapley values, it's a method from collision game theory, which actually tells us how to fairly distribute this payout among all the features. So now, what is this cooperative game theory, from where this Shapley value, the whole concept has come from? So let me just, explain this cooperative grain theory briefly with a simple example. Consider that, consider this scenario that there are three friends, Adam, Ben, and Pat. They go out for a meal, okay? So now these are the information that you have. Like if Adam is eating alone, he pays 80 bucks. Then when Ben is eating alone, he pays 56 and so on and forth. And there are some other information like if Adam and Ben both eat alone, they pay 80 bucks in total. And likewise, lastly, you see that three of them, they all eat together. When they all eat together, they pay 90 bucks in total. So just keep this information in your mind and look forward. Now your task is to figure out how much each of them should be individually, right? So this problem. In order to solve this problem, Lloyd Shepley, he is an economist. He first coined this solution in 1953, and he received his Nobel Prize. So far, I remember in 2012 for this concept. So he proposed a method for assigning payouts to players depending on their contribution to the total payout. Like the question that hit in his mind was, how should it divide a payout among a cooperative team whose members made different contributions, like the situation that we just saw for Adam, Ben, and Pete, right? Pat. So players cooperate in a coalition. So the key insights in the mind was Shapley value for member X is the amount of credit they get, and the total payout is the sum of Shapley values over members, right? So, in other words, players actually cooperate in a coalition and receive a certain profit from their cooperation. So, here, coalition is nothing but you group some of the players together, or rather, some of the features for your model together, and accomplish any particular task. So, here, the payment is the payment for the meal is the certain task. What to compute? So for every possible sub team, how much marginal value does member X add when they join to the sub team? That to be computed, right? And the Shapley value is the weighted mean of this marginal value. Fair enough. Now, can we now place these three friends with this certain concept? Like these are the information that we had previously, like Adam pays only 80 bucks when he eats alone, Ben 56, Pat 70, and Adam Ben altogether pay 80 bucks and so on and forth. So now what happens is we take all permutations of the three participants in sequence and see the incremental payout that each of them has to make, So how to do that? Now you see so here the sequence is Adam, Ben, and Pat in turn, okay? According to the given information, Adam comes and pays 80 bucks, as you can see over here, and now Adam and Ben pay 80 bucks because you see this combination when Adam and Ben, they both of them eat together, they pay 80 bucks. So Adam first ate, then he pays 80 bucks. Then the next coalition forms with Adam. Now Ben has nothing to pay, okay? And in total they pay 90 bucks. So Pat will be paying 10 bucks. So likewise, we can form all this coalition, including Adam, Ben, and Pat, right? Now you see here the position is very important. Like you see in this coalition, when Adam is coming first, Adam is paying the maximum contribution. Adam is actually giving the maximum contribution to the coalition. When Ben is coming first, Adam is in the second position, then Ben will be contributing its maximum contribution, then rest of the payout will be contributed by Adam only. So here, that's why we take all the permutations, not the combinations, because here the position is very important to form all this coalition and to compute the marginal payoffs. So moving forward, you see, if you have to calculate that, if you have to decide like how much Adam pays, for a certain case, now you see for all the permutations that we can form with Adam, Ben, and Pat, you see the marginal payoffs or the marginal contributions contributed by Adam, and you just simply take the average of this marginal payoffs. So in total, you decide that Adam will be paying 39.2 euros. So this is all about the cooperation game theory. Now you see, likewise, you repeat this task for Bain and Pat, and you can find out what is the average contribution or the payoff for both of Bain and Pat. So fine. Now, how do we relate to machine learning models with the Shapley values and this cooperative gain coalition is everything? So you see, the main connection is here the gain is nothing but the prediction task for a single instance of the data set. And the gain that you see is the difference between the actual prediction of this instance and the average prediction of all the instances that are associated with your model, right? And the players are the feature values for the instance that collaborate to receive the gain. Here, gain is nothing but the value you predict for your certain model. So you see, if your model is linear, that always life is very easy, you know. So all the coefficients that you see in the if you consider linear regression model, then all the coefficients that you see, those are nothing but it signifies the importance of your features in your in your model. But in practical, the computation is actually lengthy. So we'll just see it and how to compute those coefficients, how to compute the Shapley values, we'll see later on. Let's go back to the previous problem. Like, does Shapley actually help us with this, how to solve this problem? Now see, in your apartment example, the feature values, this park nearby, cat band, area 50 meters square, so on and forth, they work together to achieve the prediction of 300,000 euro, right? So our goal is to explain the difference between the actual prediction, which is 300 euros, 300,000 euros, and the average prediction that you see 310,000 euros, which is a difference of negative 10,000 euro, right? So, you know, using this Shapley value, you can see the answer could be like, you can say that the park nearby contributed 30,000 euros. Area 50 contributed 10,000, floor second contributed maybe 0, cat band contributed 50,000. So the overall contribution add up to negative 10,000. But we don't know exactly, right? In order to know that, we need to know the exact contribution of each of the model features, correct? So now we'll see how this can be achieved. I mean, you know, with the help of Shapley values, how we can segregate all the contributions or rather marginal payoffs, given by each of those model features. So how do we calculate this Shapley value for one feature? That is important for us. Once we know how to calculate for one feature, then it's pretty obvious that we can expose all the features within our model. So the Shapley value is the average marginal contribution of a feature value across all possible collisions. Please remember this. And we are interested in how each feature affects the prediction of a data point, right? So in a linear model, it is very much easy to calculate the individual effects, as I mentioned earlier. The coefficients basically shows the importance of any particular feature, you know. Here is what a linear model looks like. So, so this f hat x is equal to the constant part and all the coefficients and the product of the coefficient and it's the features. So the contribution for each of the feature, you can determine this as you can see here by this equation. This phi j of f hat is nothing but, you see, okay, let me just explain this equation first. So here X is nothing but the instance for which we want to contribute the contributions. Like you consider this as a data point, and this data point has p number of features, and starting from 1 through p, this x1, x2, and up till xp, these are the feature values. And this bj, the beta j is nothing but the weight corresponding to each feature j. So the contribution is phi j in total of the jth feature on the prediction f hat x. And this can be described as, or this can be expressed like this equation, where you see this E part, this E beta j xj, this is nothing but the mean effect estimate for feature j. So the contribution is the difference between the featured effect minus the average effect, you see. That's nice, fine. Now we know how much each feature contributed to the prediction, right? So if we sum all the feature contributions to for one instance, which is this x, then the result would be kind of this. So this is the estimate for one single feature, and you sum over 1 through p for all the features, and you get the ultimate feature contributions for one single instance, which is f at x minus e of f at x. But can we do the same for any type of model? That is an important question, right? So it would be great to have this as a model agnostic tool, where you don't need to bother about all the features, the domain specific features of a certain model and so on. So since we usually do not have similar weights in other model types, we need a different solution, obviously. So help actually comes from an unexpected place for us, which is cooperative game theory. The Shapley value is a solution for computing feature contributions for single predictions for any machine learning model. Now we'll see how do you compute these Shapley values. So to compute Shapley values, you just need to know how one standard collision problem or the collision game theory is defined. So in practice, in a collision game, there is a set n of, there is a set n of, this capital N you see over here, it's a set of n features, and the characteristics function you have, which is v. Now the function v has a certain meaning. What is that? It says that if S is a collision of features, this capital S is a collision of features, then v of S, you see over here, is called the worth of collision S. That means it describes the total expected sum of payoffs. The members of S is a set, and it will have a number of collisions. The set of features taking 2 or 3. You can increase or decrease the size as you want. Then the sum of payoffs of the members of S can obtain by cooperation. So you see the capital N we have, and the VS is the total, what should I say, the total, the expected payoff. And this is a very important feature. You see that each feature demanding their contribution as a fair compensation. I'll explain it later on with a simple example. Now you see from the previous equation, the Shapley value is actually so the Shapley value is one way to distribute the total gains of the feature, right? So assuming that they all collaborate. That means we assume that each of the feature are actually participating in the game of prediction, and we need to identify the individual gain obtained for each of them, right? So according to Shapley value, the amount the feature I gets given a collision gain, which is from this equation, right? You see, we have taken all the permutations from the collision set, which was S, and we try to integrate the target feature, as you can see, which is I, and we take out the difference between this union and all other permutations that you have, and you sum over through R. R here is the orders, yes. R is the ordering of the feature, and this P, RPI is a set of features in N which precede I in the order R. As I already mentioned here, the sequence is very important. That's why we take always the permutation. Now, so ultimately you can express the the Shapley value for this feature vector V is like 1 upon number of features, and you sum over all the conditions excluding I, and you take the ratio marginal contribution of I, which is the target feature for your model, to collision, and the number of collision excluding I of this size. So let's try to solve this simple problem. I'm giving a problem like it's called a glove problem, that and you need to settle down all the team members, the objective function using computing the Shapley value. So what's that? This problem says that you have there are three players. Players have left and right hand gloves, and the goal is to form pairs. You have to form some pairs from all the players that you have in your team. Now you need to, for making this, forming these teams, you need to compute the Shapley values. For example, the task is to compute Shapley values for the member A, okay? So we have defined this large N, the set of features that you have, A, B, C, there are three features, and V, the characteristic function with all the collisions that you have. How they're defined is S is a set consisting of these three collisions you have currently. The first set is having two features, AC, then BC, and the ABC is the third set that is that are in the collision set. Now you define the characteristic function value like this. Now, if it signifies that if the collision is in between this set S, then the corresponding value would be 1, otherwise it would be 0. So just to remind you how we calculate the collision, I've just put this equation here. I would like to give you 2 minutes to, think about the solution, like how to compute the Shapley value for this player R or the feature R. That means in which team it will be contributing the maximum payoff or the minimum payoff. Let's go back to the previous problem with this Adam, Ben, and Pat. I think that would be helpful for you to think about it. I'll help you to, figure out the answers, but let me just give you, just think for a while and try to come up with a solution. Like if that helps, if this equation helps to compute the Shapley value for this player A, sorry. So let's move ahead. So you see, this was our problem. We have a set N with 3 features, and we have 3 different collisions, and the collision set is large S, and we define this characteristic function value like this, So this is the equation, this is how we compute the Shapley value. Now you see, out of these 3 features, A, B, C, how many different orderings we may have? We have factorial 3. The factorial n number of orderings we can have. So these are the orderings that I have written over here. Okay. Now you see, A is coming first in this first ordering. So the payoff, the maximum payoff will be paid by the player A only, right? So if you look at this expression V of RPI union I, here RPI is actually a null set. is actually giving you null, because A is coming first, and you union this with this I is nothing but A over here, and you see you have to subtract this V of RPI, which is nothing but a null. Why? Because A doesn't belong to this collision set. A has come first, and there's no collision occurred. Yes, I mean yet, right? But in the next very case, you see A has come first, and I mean, still the same case here. There is no collision as of now. But in the third case, you see B has come first, then comes A. And please, I mean, remember that we are trying to find out the Shapley value for this player A, right? So here the first collision occurs with A and B. Now you see, you try to find out that where this collision present in the set S or not, right? So the first collision is A and B. It doesn't belong to this set S. So that means you have to give this value 0 to this collision. And then you subtract this part, V of RPI. So so for I mean the B precedes B precedes A, so the value of VB would be 0. So 0 minus 0 0. So likewise you compute all the payoffs, I mean the marginal computation for the player A, and ultimately you at the end you sum, you get this, right? This 1 by 6 is nothing but 1 by n factorial, which is 1 by 6, and you sum over all the order, I mean all the marginal contribution contributed by this player A, and you sum over for all the orderings, right? So if you sum this these outcomes, you get 1. So ultimately the marginal payoff or the Shapley value that we computed for this player A is 1 by 6. Likewise, you can compute for player B and C. Now let's go back to the previous problem. Now I hope you can form all the collisions. You can increase the size of the collisions one by one. You see, this is the null set. That is, there's no collision and no features at all. Now you take you take one feature at a time, and you form the collision set, and gradually increase the set, I mean the size of the collision, and you populate the set of collisions. So thus, with these 8 collisions are actually needed for computing the exact Shapley value for the cat band feature value. If you have all the informations that I have given like this, like the characteristics function, the contribution of each of the collision in the model, and then you can compute the Shapley value for one particular feature. So these are a few resources regarding Shapley values that might be of interest to you. This is a very good book, like An Unified Approach for Interpreting Model Predictions. I would suggest to go through this book if you're interested in it. Now let's move on to SHAP, which is Shapley Additive Explanations. So the goal of SHAP actually was to explain the prediction of an instance X, like one data point having different features, by computing the contributions of each feature to the prediction. The SHAP explanation, this SHAP explanation method actually computes Shapley values from collision game theory, as I already explained. The feature values of a data instance act as players in a collision. Shapley values tell us how to fairly distribute the payout, that is the prediction among the features. Here, a player can be an individual feature value. For example, if you consider the tabular data, or a player can also be a group of feature values. For example, if you take an example, if you are to explain an image, pixels can be grouped of superpixels and the prediction distributed among them. So one innovation that SHAP brings to the table is that the Shapley values explanation is presented as an additive feature attribution method, in a linear model. And the view connects both Lime and Shepley values all together. You have a brief overview about Lime earlier this morning from Devashish's talk. And I'm not going to explain Lime over here right now, but I'll definitely show you how SHAP package is used for interpreting your model taking a simple example. So initially, the authors like Lundberg and Lee in 2016, they proposed kernel SHAP as an alternative kernel SHAP estimation approach for Shapley values, which was inspired by local surrogate models. Quite similar to Lime. And the authors also proposed tree SHAP, a variant of SHAP for tree-based machine learning models such as decision trees, random forest, gradient boostings. They proposed gradient boosted trees, and the tree SHAP was introduced as a fast model-specific alternative to kernel SHAP. But it turned out that it can produce unintuitive feature attributions. So I'll just way forward, you can see that the authors like Lundberg and Lee, they implemented SHAP in the SHAP Python package, which I'm going to show you shortly. And the works for tree-based models in the scikit-learn in the machine. They work for tree-based models in the scikit-learn machine learning library for Python. You can also find out there. They have integrated into the tree boosting frameworks, XGBoost, the gradient boosting, and the light GBM. And in R, those who were very much enthusiastic with R, there is a Shaper and Fast SHAP packages. SHAP is also included in the R XGBoost package. Pardon, I haven't used these packages though, but I'm going to show you how you can interpret your model, the features, the interpretability using SHAP Python package. So for those who are interested in SHAP, to incorporate SHAP into your model explanation, these are the resources that would be worth going through. Okay. So for my slides and images, I have used these resources mostly. Now I would like to show you some example with SHAP packages. Let me just open my notebook first. I hope it's visible to everyone.
Yes, ma'am.
Okay, great. So here you see, we train a linear regression model on the classical Boston housing dataset. We have used this dataset for explaining a model. The dataset consists of 5, not 6, neighborhood regions around Boston in 1978, where our goal is to predict the median house price in thousands in each neighborhood from 14 different features. So you see, these are the different features that you have. So our objective, is to find out, how to interpret one model using different interpretation or the Shapley values that we compute from a certain plots and different kind of interpretability metrics that we have, how to interpret our model itself. Now, let me just run this. So here you see, I'll be explaining the interpretability using one very simple model, which is linear regression. You see, we have just taken the data set. We've just read the data set. There are 100 instances for using the background distribution. And this is a simple linear regression model that we're fitting into. So now you examine the model coefficients. You see there are several coefficients you see out of, I mean, they're listed over here, and you see the model coefficients. As I told you, in the linear regression model, or the model coefficients is nothing but it tells you the importance of each and every feature, right? But the I mean, in the most common way of understanding a linear model is to examine the coefficients obviously learned for each feature. So these coefficients tell us how much the model output changes actually when we change each of the feature, I mean, in input features, right? But while coefficients are great for telling us what will happen when we change the value of an input features by themselves, they're not a very great way to measure the overall importance of a feature, I believe. So this is because the value of each coefficient depends on the scale of the input features. If, for example, we were to measure the age of a home in minutes instead of years, then the coefficients of the age feature would become large, right? If you convert this year to, to minutes. Clearly, the number of minutes since the house was built is not more important than the number of years, yet its coefficient value is much larger, right? So that means the magnitude of a coefficient is not necessarily a good measure of a feature's importance in a linear model. So let's have a more complete picture using partial dependence plot, how it works, what it tells us. You see the graph over here. We know that to understand a feature's importance in a model, it is always necessary to understand, both, how changing that features impacts the model output, and also the distribution of that features values. So to visualize this, for a linear model, we can build a classical partial dependence plot like this, and um, and we can show the distribution of feature values at a histogram on the x-axis. You see this histogram over here. The gray horizontal line that you see in the plot is in the plot. This actually represents the expected value of the model when applied to the Boston housing dataset that we're dealing with. The vertical gray line you see over here, this represents the average value of the age feature here, because we have considered the age feature here only. Note that the blue partial dependence, this line, this plot, which is the average value of the model output when we fix the age feature to a given value. It always passes through the interaction of the true gray expected, this is the expected output you expect for this model, the data point fx. Now we can consider the intersection point as the center of the partial dependence plot with respect to the data distribution. So the impact of the centering will become clear when we turn to Shapley values next. Uh, Next, we try to read Shapley values from partial dependence plots. How to read it, you see. I'm sorry, let me run this again. Let me just run this again. It's going to take a while. That's not running. Apologies, it's just taking a while. I don't know why. Just let me just stop sharing. That will work, I guess. Just give me a minute. I'm sorry for the delay. You see, I'm running this SHAP package and I'm calling this explainer function just to see the partial dependence plot. I mean, the reading the Shapley values from the partial dependence plot. Oh, thank God. It yeah, it's visible, right? So you see how to read the SHAP values from partial dependence plots. It's like the SHAP values can be very complicated to compute sometimes, but this linear model is so simple that we can read the SHAP values right off a partial dependence plot always. That's why I'm showing you this partial dependence plots. Now, when we're explaining a prediction like for fx, for this one, the SHAP value for a specific feature I is just the difference between that. You see this red inked point, like this is your the dependence plot, and this is the expected output that you were expecting from your model, and this actually defines the difference between the expected model output and the partial dependence plot, which is nothing but the Shapley values tells you. So next we have a close correspondence between the classical partial dependence plot and the the SHAP values. That means that if you plot the SHAP values for a specific feature across a whole document set, will actually get an exact trace out a mean-centered version of the partial dependence plot for the feature. So all the dotted points that you see over here, these are the Shapley values that you plot, and you get the partial dependence plot in return. So next we see the waterfall model. This is an additive nature of Shapley values. So you see here all the feature values that were there in the data set. Now we start from this expected output, which is 22.841, and this is the feature value, that is the 16.17. And this waterfall model, in case of SHAP, the SHAP values are SHAP values of all the input features is always sum up to the difference between the baseline expected. Like this is your expected baseline, and this is what you are getting actually, this fx. And the current model output of the predicting being explained by this waterfall model. And the easiest way to see this is through a waterfall plot. Why? Because it starts our background prior expectation for home price, for example, this E of fx starting from 22.84, and then it adds all the features one by one at a time until we reach the current model output, which is fx. So this red features, the red inked lines that you see here, that are actually adding some positive vibe and the positive value to your model outcome, and these are actually negative. So these are important. This tells you which features are important for your model and which are not. That's all about waterfall plot. Next, another very interesting plot is beesworm. I hope this runs. This is nothing but this is also known as the summary plot. This combines this feature importance with feature effects actually. So each point on the summary plot, or this beesworm plot you see here, is a Shapley value for a feature and an instance for a data instance. So the position of the y-axis is determined by the feature, and on the x-axis by the Shapley value. And the color represents, you see, let me just show you. this base one. Yeah, this plot I'm talking about. So the color represents the value of the feature from low to high. You see, this is the indication that these are the feature with low values and it's going to high gradually. So the overlapping points are actually, all these overlapping points are actually jittered in y-axis direction. So we get a sense of the distribution of the Shapley values per feature. The features are ordered according to their importance, like I said, I mean, this line indicates. So that was all for a very simple model, which is the linear regression model. And as I already told you, there are two segments like kernel SHAP and the tree SHAP. So all the tree SHAP models are actually applicable for this kind of tree-based models like XBoost or GBM, whatever. So you see, I have just put one example for XBoost, like the you see here, like these are not the linear models. So for every data points, I mean for every features, you find out the difference between the expected value and the actual outcome of the feature. And by using the Shapley value here also, you can get this the scatter plot, and you can have this beesworm plot, and you can see how your features is actually working out inside the model. So I think that was all. You can try out with some other complex models as well. This is a very, very powerful package that has been introduced by these two authors lately. So I think that's all from my side. And for further readings for both Shapley values and the SHAP packages, you can go through these resources if you're interested. And that's all. Thank you. Thank you so much for your patience. If you have any questions, I'm already ready to answer your questions.
Thank you so much, Suchana, for this excellent walkthrough of SHAP. Devasis, is there anything that your group is going to be covering further, or are we done with all the content?
No, I guess we are done from our side. So I was hoping that we could have a question answering session, where we had 3 talks running.
Sure.
So that gave some time for the audience to think about some of the questions, and then if they want to shoot some questions to any of us, we are happy to answer.
Folks, this is your opportunity. Devasis and the other speakers today are experts in explainability, and it's your opportunity to really ask them questions and make sure that the understanding you have gained today is going to stay with you. Looks like they've had 5 fairly strenuous days, Devasis. So
I can understand, yeah.
But thank you so much to you and your team for doing this. Without, I think, the speakers that have so kindly given their time here, this masterclass could not have been held. And I really do appreciate the fact that I know that this is, the different time zone and everything comes into play here. And we really appreciate that you've once again supported the masterclass as you did the last time. So thank you.
Thanks a lot. Thanks a lot for inviting me and giving me an opportunity again to speak. And it's also a very good opportunity for the students of mine, to speak at this platform, and then talk about some of their own research and maybe some of the challenges, in explainability and in AI, and some of their thoughts as well. So it's a good platform for them, I believe. So thanks a lot.
Absolutely. Thank you. And Procheta, thank you as well for the time that you spent on this.
Thank you. Thank you very much.
Thanks.
So folks, this brings us to the end of the masterclass. And, I want to thank all of you to have taken the time out and spent your weekends learning. I hope this has added a lot of value to your skills within the space of deep learning and machine learning in general and data science. We've tried to create a program that gives you a flavor of what it means to deal with all sorts of unstructured data, text, images, speech. And we've also explored a number of different architectures. And I think explainability is one of the hottest areas in deep learning. And I'm glad that we've been able to spend today on, as I saw a comment from Braj, that it's a very different set of topics that were covered today, right? The fact that we spent a lot of time on explainability, but prior to that also Vikas Agarwal talking about how it's different, to try and solve problems for large corporations, right? And how it takes a lot more than applying machine learning algorithms, because you have to understand the context, the business context of it. And this whole area, Vikas was talking about how all of the models that we typically use in machine learning are all correlation based, and how causality is something that is not hasn't kind of created this its place, right, in applications at least. Of course, we've been talking about it in academia for a long time, but I think center stage currently still remains with models that are very focused on correlations, and how that limits the kinds of inferences we can make. And I think that's a very important piece that I hope that all the attendees have taken away from this. For the attendees, I wanted to let you know that there are these problems that we have set for you, the 3 pieces of coursework, and I hope that you're making good progress on that. There are 2 types of certifications. One is obviously for participation, and I congratulate all of you who have come to attend this whole 5-day program. But also, I think there is the 2 certificates we have. One is for participation, and one is in excelling on the pieces of coursework. So you're going to be given 10 days to work on these problems that we have set you. We are in the process of setting up a private Kaggle competition page, where you would be asked to make predictions on a test data set and upload those. And really, it depends on how well your models perform, whether you get your participation certificate or actually a certificate of excellence. Of course, like I said earlier, this is only the start of this journey. And I hope that you're going to remain connected with us. We are here to help you and mentor you and help you in whatever way you need to be able to create a place for yourself in industry as data scientists. And this is our small attempt at making sure that the kind of skilling that's required, the deep skilling that's required in this space in India, is being provided to those who are interested in learning this. What I do want to do is to thank every one of the speakers that took out time. It's not easy for the speakers to take out time from their daily routines and to come and spend time, prepare the material. And starting from day 1, where we had Professor Bhiksha Raj from Carnegie Mellon, who came and gave a talk to you on what is machine learning and set up the scene for the rest of the masterclass. I'd like to thank Devanjali as well for working at the basics of image processing. Partho, my colleague from Tatras, who spoke to you about speech processing. Of course, Professor Saurabh Hussain from BMU, who took on the mantle for the second day and walked you through multi-layered perceptrons. And my colleague Gurmukh and other colleagues, Jayabrata and Bapaditya, who then on day 3 worked through the convolutional neural networks, followed then by Dipanjan Sarkar on day 4, who did the session on attention and transformers. And then, like I said, today, an excellent set of sessions started off by Vikas, then again Partho. I spent time with you, hopefully giving you an insight into the problem sets that we've set for you and how to address those with deep learning. And then, of course, Devasis and Suchana and Procheta, who did a fantastic job of covering explainability. In addition to that, I'd like to introduce to you all my two pillars, without whom I think none of this could have happened, and that's Tavleen and Nampreet. Tavleen and Nampreet, I think you should switch on your cameras and take a bow. You've been amazing at making sure that everything has run seamlessly here. And you've really done a great job. It's not easy to deal with the number of applications we had and to make sure that we have all the sessions running on time. You looked after all the queries, and I really appreciate the hard work that you've done. I'd also like you, Tavleen, to introduce the others in your team that have supported you. Of course, I know behind every speaker or organizer, there's always a team of people. So if you can unmute and just introduce the people that also helped you in delivering this.
Yes, sir. So we had a team of 3, Abhishek, Ananya, and Kritika with us, and they have been helping us throughout, and we are really lucky to have them in our team. So if you could please switch on your cameras as well, if you are really in the shape to do that.
I think they are not.
Okay, okay. So we should have prepared them earlier, huh? So thank you for that. And I know at least Akshay and Gurjot have been working in the background. And who else was there? Tavleen and Nampreet from the Sabud team.
Sir,
on the technical support.
Yes, sir. Sir Neetu ma'am, yeah. Then Sarabjeet, Nupur, these
Wonderful.
3, then Mananjot. Yeah.
Wonderful. So thank you to all of them as well. We have, I believe, Tavleen, you've made available on EducoLab a form for feedback on all the sessions. I think for us also, we see these as opportunities to learn from these sessions and to learn what we can do better to bring you the kind of support and learning that we are trying to bring to you. So I would request you all, and of course we will share this with all of the participants, even if those who have not been able to make it to the last couple of sessions, so that we can hear from them also. We have had a few people that started and we lost along the way. We want to hear from them, more importantly, as to what we could have done to support their learning more. So we will be reaching out to them as well, because it is a learning process, and I think especially in this environment like we have today, where everything's happening online rather than face-to-face, I think there are incredible positives to that. The fact that we have Devasis beaming in from Glasgow, I think, is it Suchana or one of your PhD students from Dublin, right? Devasis, who's also presenting here.
Yeah, that's
so yeah, great. So Dublin is one of my favorite cities. I'm jealous that you're there. I've spent many an evening there, which are wonderful, have been wonderful evenings. So I think Bhiksha Raj was able to beam in from Carnegie Mellon, and this is a great advantage. But I do understand that when people are trying to learn online, it is more difficult than in face-to-face scenarios. So congratulations to all of the students that have got to the end of this program. Before I sign off, I'd like Saurabh, my colleague from BML Munjal University. Saurabh, if you can just maybe say a few words. I'd like to thank you for the support that you have given this program. This is obviously a program that has been run in collaboration with BML Munjal University. And Saurabh, if you can maybe just say a few words.
Sure, sir. Thank you. So I would like to thank all the speakers, and you have sort of summarized what we have done in this master's course. And thanks to all the speakers, all the keynote speakers, all those people who have taken all the sessions, those who have actually conducted it at the background, right? I see that there are volunteers from Sabooth who are constantly in touch with the participants through these WhatsApp chats and sending mails and resolving their queries. Okay, so I do hope that it has actually helped all the participants. And this is, as Sarabjot sir has already mentioned, right? This is just the starting point. But I hope that you have been able to learn something meaningful. And we do hope that this type of effort will be appreciated, and then our participants are actually learning something meaningful from it. So thank you, all the participants. And we need some time to evaluate the assignments. And after that, we'll be distributing the certificates. Anything else you would like to mention, Sarabjot sir, apart from whatever you have already mentioned?
No, like I said, this is the start. You will have access to EduCollab for the rest of your lives. And so by all means, continue to dip into the content. I know it's a lot to consume in 5 days. People like Saurabh and, a lot of the speakers here also, and myself, we've spent decades in this space. And, condensing it in 5 days is unfair on you all. There's a lot of information to learn here. So I hope that you see this as a starting point and are excited about dipping into more of the content. And if you need any support from Sabooth or from BML Munjal University, we'll be very happy to provide that to you. So best of luck. And, we hope that we can be part of your journey going forward in the future as well. So take care, everyone. Goodbye.
Thank you. Bye-bye.
Goodbye. Thank you.